All right, so in talking about atomic emission, this was all figured out by a guy named Bohr, Niels Bohr. Sometimes people pronounce it Niels Bohr. I've heard it pronounced multiple different ways. A dude named Bohr, okay? He did a lot of experimentation with the hydrogen atom and figured out from the hydrogen atom, like if you excite electrons, they're going to absorb energy and they're going to jump up energy levels like what we have here. They're going to jump up energy levels. But that excited state isn't going to maintain. The electron will fall back down. Whatever goes up must come down. It will fall back down. So, and when it falls back down, it emits a photon in the form of electromagnetic radiation. We talked about that a little bit last time, talking about how like the different colors come from the different frequencies of the photons being released. So this is absorption. This is a positive. We're increasing the energy. When we emit energy, it is a negative, okay, in terms of energy. The different energy level transition, so n equals 1, n equals 2, n equals 3, n equals 4, those numbers, those are the energy levels. Remember, in an atom, electrons are arranged first in energy levels. The energy levels are divided into sublevels. Each type of sublevel has a different number of orbitals. We'll review those bits and pieces in a little bit. But for right now, we're just talking broad energy levels, okay? So the different energy level transitions will give off different frequencies of light, okay? And if we're looking at visible light, it'll give off different colors of light. In 2 classes, which I believe will be Friday for you guys, we're going to do a lab where we're going to look at more periodic trend stuff, but I'm also going to set up these gas tubes they're glass tubes that have different gases in them. One of them might be like oxygen gas, another one might be nitrogen, hydrogen, different types of gases. And we're going to look at them using a spectroscope, so you'll actually be able to see the emission spectrum like what we have here of the different gases. You'll see different lines for different colors for the different gases. Every gas will have its own unique emission spectrum, okay, because it all depends on what orbitals are available or what energy levels are available in that atom and how many electrons it has, what electrons are being excited, all that stuff, okay? So we're going to talk more about the emission spectra on that day, okay? But right now, let's just talk about the transitions. If it's jumping up energy levels, it's absorbing energy, it's a positive delta E. If it's dropping down energy levels, it's emitting energy, it's a negative delta E. All right. If we look at it in terms of more three-dimensional, we have this picture. This still is not a three-dimensional picture, but remember, the energy levels are surrounding the nucleus. This right here is my nucleus. All right. The energy levels are surrounding. Oops, that's not my nucleus. My nucleus isn't drawn here. I just realized. This is energy level 1. My nucleus is like here. Okay. So 1, 2, 3, 4, 5. All right. So the different energy levels are surrounding that nucleus. If we're falling towards the nucleus, it's emission. If we're moving away from the nucleus, it's absorption. Okay. And like I said, the different energy level transitions will give those different colors of light. Right, now this was all done with the hydrogen atom. Once you start adding in, once you start like looking at other atoms that have more electrons, you're adding in another component because those electrons, in those atoms with more than one electron, you now have repulsion forces going on, and it will manipulate it, and it won't work out as well, but we just make the assumption that the formula we're about to look at works for everything. It really only works for the hydrogen atom, though. Okay? And the formula, and this is in your guided notes, it's called the Rydberg equation. All right? I do not want you to memorize this. Okay, I do not want you to memorize that formula. Okay? We're going to use it in the next couple of problems, and there's problems in your homework that ask you to use the formula, but at no point should you memorize it. Okay? I'm pretty sure it's in your guided notes. No, it's, okay, yeah, that works. It is the same thing. Z squared for hydrogen would be 1, because Z is the number of protons. Hydrogen only has 1, so it'd be 1 squared, which is 1. Yeah, that's why. I don't know why that one doesn't have a difference. I thought this was in your guided notes. I apologize. Well, write it in your in-class problems. You're going to need that formula for your homework, okay? So, the negative 2.178 times 10 to the negative 18 joules is a constant, okay? And then in the subtraction, we're going to take 1 over n final squared. N final is the energy level where the electron is ending, where it's ending up, okay? And we're going to square that number. The n's will be integers. 1, 2, 3, 4, 5, 6, 7. So square it, and then minus 1 over n initial squared. N initial is where the electron starts, okay? So remember, when we are, in mathematically, and you'll see this in your homework and in the next problem we do, mathematically it works out that when you're increasing energy levels, when you're going from like energy level 1 to say 5, this whole problem, this whole delta E ends up being positive. And that makes sense because you're absorbing energy. And when you're dropping down energy levels, say from like 5 to 2, this answer is going to be negative because you're releasing energy. Okay, the sign of delta E just tells you if the electron is jumping up energy levels or falling down energy levels. Okay? Kind of like with thermodynamics, it just tells you the direction of the transfer. Okay. So let's look at this problem. We're going to figure out the color of light. We're actually not going to figure out the color of light because I don't require you to memorize that like 700 nanometers is red light and 400 nanometers is violet light. Like you don't need to memorize that. We're more going to compare the energies of the light to tell us which one's more towards the red end, which one's more towards the violet end. Okay? So we have the hydrogen atom. We've excited its electron. It is going to fall from n equals 5 to n equals 2. We're going to calculate the delta E for that. And that excited electron is going to fall from 3 to 2. So it's like 2 different experiments with it, seeing what's going on with that electron. Okay? So, delta E equals negative 2.178 times 10 to the negative 18 joules. Remember, do not memorize this. 1 over n final squared. What is n final? 2, and then so 2 squared, minus 1 over n initial squared. What's n initial? 5 squared. Is this absorption or emission? Emission. I mean, it literally says right here, emitted, and the fact that it's falling. So what sign will our delta E have? Negative. And mathematically, that should end up being negative because we have a negative in front of the whole thing. 1 over 2 squared minus 1 over 5 squared will end up being a positive value. Okay? So go ahead and do that math so we can get the energy amount. Because you're never going to be asked to do a calculation like this on the AP exam. And if I ask you to do a calculation like this on your test, I will give you the formula. All right, what is the delta E for this electron? 4.57 times 10 to the negative 19? What's your unit? Joules. Okay. And then we could convert that to wavelength using E equals hc over lambda, which that is a formula that I suggest you memorize. It's just a combination of the two formulas that are on your formula sheet. but it sometimes is helpful to have that one already known. I'm sure it has a name. I can't think of it right now. All right, so then let's calculate the energy for the other electron's transition, or the other transition of that electron. So let's set up the problem. Where is this electron ending? The 2, same place as the last one, but it's starting at the 3rd energy level instead of the 5th. What will our sign be? Negative. It's still negative. We still are falling, or our electron is still being, no, our electron is still falling. A photon is still being emitted. Before you give me the answer for the math, do you expect the amount of energy being emitted to be greater than, less than, or equal to the amount of energy being emitted for the first transition? Why do you say it's less? Exactly. Where it's falling a shorter distance, so the amount of energy it gets out should be less. Okay, and what is it? I just rounded to 3 sig figs. Negative 3.03 times 10 to the negative 19. Remember, what does the negative sign tell us? Emission, that the electron is falling energy levels. So we really just need to compare the absolute values of these numbers. Oh, yep, look, the electron for that second transition is emitting less energy. It's more of the conceptual part of this that you need to worry about. So an electron traveling a shorter distance will emit a light with less energy. Okay, that's the part you need to know. So now, in terms of wavelength, remember, what's the relationship between energy and wavelength? Indirect. The shorter the wavelength, the higher the energy. So the fact that our first transition has more energy, this will have a shorter wavelength, and this will have a longer wavelength. So we kind of answered the second part of this. The one with the longest wavelength of light will be the second transition. So in terms of visible light, the one with the shorter wavelength will be closer to the violet end of the visible spectrum. And the one with the longer wavelength will be closer to the red end. Okay? So if this were a question on the AP exam, you wouldn't need to actually go through the whole calculation of delta E. You would just need to know that, oh, N3 to N2, that's a shorter transition, so it would emit light with a longer wavelength because it's less energy. Okay? So you could totally, we honestly could have totally answered this question without doing the math behind it. I just wanted to show you the math. Okay? All right. So now we're going to move into electron arrangement. Okay? We're going to move into electron arrangement. Before we do that, though, before we answer number 7, let me insert a page, and I'm going to go through some review of electron arrangements. Okay? So remember, energy level, that's like the broadest description for where the electrons live. Actually, the electron cloud would be the broadest description. And in that electron cloud, we have these different energy levels. How many energy levels do we have? There's technically infinity energy levels, but we don't have any electrons that utilize more than 7. Okay? So we are just really going to deal with 1 through 7. But technically, there's an infinite number. But yeah. So energy levels, they are divided into what? Sublevels or subshells. Depending upon the textbook, you might see it as, or the source for the question. Sometimes they're called subshells, sometimes they're called sublevels, because energy levels are sometimes called like shells. So either one. Okay, just be aware that you might see it one way or the other. What are our sublevels called? S, P, D, and F. And they have names. It's like sharp, principal, diffuse, and I can never remember what F stands for. But they actually, like, there's like real names for it. And it's all physics. It's magic. It's that physics that we don't like to discuss. All right. We'll talk about S, P, D, and F and how and that stuff in just a little bit. Sublevels are divided into what? Orbitals. And the number of orbitals on the sublevel depends on the type of sublevel. And then how many electrons in each orbital? 2 electrons max. How do those electrons go in the orbitals? Opposite spin. Okay? So, just dividing this off so it doesn't get all mixed up. So let's talk about the sublevels. We have S, P, D, and F. We're going to look at the number of orbitals. And the number of electrons in each one of those sublevels. All right. In the S sublevel, how many orbitals are there? 1 orbital. So how many electrons can be on the S sublevel? 2. The P sublevel, how many orbitals are there? 3. So how many electrons? 6. D sublevel, 5. How many electrons? And F. 7 orbitals. 1, 3, 5, 7. How many electrons? 14. The S sublevel is found on which energy levels? Yes, the first, the second. Always the third. Always all of them. They're going to be found on n equals 1 through 7. So the S sublevel is always the first sublevel that is filled for that energy level because it has the lowest energy. The shape of the S sublevel is a sphere. Okay, that's not why it's called the S sublevel. It just happens to, they both start with the same letter, okay? The P sublevel is found on which energy levels? 2 through 7. Anyone know what this shape is called? Yeah, it's called a dumbbell. But yeah, so it looks kind of like a figure 8. Now, these are the shapes of the individual orbitals. It just happens that the S sublevel only has the 1 orbital. But there are 3 P orbitals that have a dumbbell shape. Okay? But those dumbbell shapes are in 3 different orientations. One will be, so let me draw it over here. One will be going along the y-axis, another one will be going along the x-axis, and then another one will be kind of going along the z-axis. So it's just different orientations in space. So this would be P sub y, this would be P sub x, this would be P sub z. Okay, just be aware that there's just They're just different orientations in space. Your guided notes in your textbook have much better pictures than what I just drew. Okay? The D sublevel is on what energy levels? 3 through 7. And I'm not even going to attempt to draw these. These are much more complex. But again, they're going to be oriented in space a little bit differently. Okay? And then the F sublevel, 4 through 7. And again, these pictures are these orbitals are even more complex in shape. The more complex the shape, the more energy the electron needs to have in order to live in that orbital. Okay? Which is why the Aufbau principle is that you need to fill from the bottom up. Okay? Electrons will enter the lowest energy orbital that's available, or the orbital with the lowest amount of energy available. Okay? So before we get into electron arrangement, let's just do a couple practice problems with this. So, what is the maximum number of electrons in these things? So in a 2s sublevel, what is the maximum number of electrons? How many? 2. The fact that it's a 2s. The big number in front just tells which energy level, it's kind of like which floor that sublevel is found on. It's an S sublevel, it can only hold 2 electrons. What about a 3D sublevel? 10. D is 10. And what about on the whole 4th energy level, the entire 4th energy level? How many electrons can be found there? How'd you get that number? And what sublevels are available? All 4 different types of sublevels are available on the 4th energy level. 2, 6, 10, and 14 equals 32. There's actually a mathematical formula for calculating the theoretical number of electrons that could be found on an energy level. And that is 2n squared. So you take the energy level and number, remember they're always integers, 1, 2, 3, whatever. You square it and then you multiply it by 2. But that's the theoretical number. It's not necessarily what happens IRL. Okay? It's not necessarily what happens in real life. So like the 5th energy level, what's 5 squared? 25 times 2, 50. Technically, the 5th energy level could have 50 electrons, but we just don't have sublevels past, we don't have elements that use sublevels past F. Okay. All right, and what about the 2p orbital? How many of you think it's 6? If you think it's 6, you're getting tricked. What's the key word here? Orbital. How many electrons are allowed in any orbital? 2. That's it. Just 2 in any orbital. So don't get thrown off. Like, this is a great multiple choice type question. Don't get tricked. Doesn't matter if it's 2p, if it's 1s, if it's 4d, whatever. The fact that it's an orbital, only 2 electrons. Okay? All right. So, I am going to add in another page, and I don't remember if this was in your guided notes or not, but I suggest you draw this off to the side. I am drawing what is called the diagonal rule. That's just kind of a trick to remember the direction and the order that the electrons fill. You can use this, or you can use the periodic table, or use them both together. Depending upon how you learned electron configurations and stuff like that, you might have learned it based off of the periodic table. You might have learned it based off of this. So just a couple different ways to learn this, okay? When I teach this to my academic kids, I have them learn I teach them this first, the diagonal rule first, and then I show how it corresponds to the periodic table, okay? So either one. So it's called the diagonal rule because the electrons will fill these orbitals in a diagonal fashion, meaning we hit the 1s first, and then the 2s, and these are supposed to be parallel lines. I just can't draw today. So it's showing how after 3p, we then have to fill the 4s, and then we pick up 3d. That is because, like, for example, 4s and 3d. 4s has slightly lower energy than 3d. Even though it's on the next energy level up, it has slightly lower energy. So after electrons fill 3p, the next one, it chooses between the 4s and the 3d. It's like, oh, I'm going to live where it takes less energy, right? Because remember, things like to have minimal energy. Things like to use minimal energy, okay? And then after 3d, we continue 4p, 5s. So kind of, and same thing what happens with the f. 4f doesn't get filled until after 5p and 6s. Remember, those f orbitals are very complex in shape, okay? And we always start down at the 1s. Oops. All right. How are we doing with that? Are you guys done drawing that? Okay, so now let's do some practice. So we're going to start with electron configurations. That's like the 1s2, 2s2, 2p, whatever, okay? I'm not going to, we will probably never draw a complete orbital diagram. When we draw an orbital diagram, we're really only going to be looking at the valence part, because that's the important part. Okay, but for right now, let's write out the expected electron configurations for these things, okay? So for sulfur, how many electrons do we have? 16. We just look at the atomic number, and that's the number of electrons. We only have to worry about ions later, okay? So 16 electrons. So where do we start? 1s, 2. Then 2s, 2. 2p6, 3s2, 3p4. And it's done. Questions? Okay. We're going to do the full for barium, and then for europium, I will review the noble gas configuration, which is also called the core configuration. Barium, how many electrons? 56. I apologize. It's okay. Later on, you'll do bismuth and platinum. Bismuth has 83. Platinum has 78. All right, where do we start? 1s2. So it's basically going to be sulfur and then more stuff, right? 2s2, 2p6, 3s2, 3p6. Because sulfur had to end at 3p4 because we were out of electrons at that point. After 3p comes 4s, not 3d. 3d comes after 4s. And then 4p6. What comes after 4p? 5s2. What comes after 5s? 4d10. Then 5p6. 6s2. And we're done! Yay! Now technically, from this all the way to here is the configuration for what element? Xenon. That is the configuration for xenon. So we could have just done this. That is called the noble gas configuration or the core configuration. Called the same thing. Core is referring to the core electrons. They're the electrons that aren't valence. Okay? So the way to remember the way to figure out which noble gas to use, you can only use a noble gas for the noble gas configuration. Remember, the way to figure it out, I tell my kids, it's Price is Right rules. All right? You have to get the closest in atomic number to whatever element you're looking at without going over. Okay? So for europium, its atomic number is 63. What is the closest noble gas to 63 without being greater than it? Remember, the noble gases are group 18. There's one closer to 63. Xenon. Radon is over it, so you can't use it. So you have to use xenon. So xenon, we just figured out the xenon's configuration ends at 5p6. What comes after 5p6? Oh, 6s2. So we now have 54, 56 electrons. That's basically barium. We have 56. We need how many more? 7. So what comes after 6s2? 4f7. Now, if you're using the periodic table, we did that just based off of the number of electrons. If you're using the periodic table, you would see that it is, you might have gotten this, Xe, 6s2, and then 5d1, and then 4f7. There's a lot of weirdness that happens with the F block elements because of lanthanum and actinium are technically in the D block, but it's because the energies of those orbitals are all very, very close together. Okay? I would accept either one of those. Oh, not 4f7. Sorry about that. 4f6. I will accept either of those answers. It is really this. Okay? So, you're going to do a little bit of practice on your own. I'm going to pause this. You have 1, 2, 3, 4. You have 5 things there that I want you to write the full configuration and then the core configuration. All right, so here are the full configuration and core configurations for those 5 elements. All right. If this is something that you need to review more, correct me if I'm wrong, but I'm pretty sure that in the Flynn prep course you had to do during the summer, it went over this stuff, right? I know it's been like since the summer that you looked at it, but you got a year-long license for that. So feel free to go back and redo like the practice stuff within that. Look at the notes that they have. You can also look on, you can look at your Chem 1 notes if you still have them. Hopefully you do because you were taking AP Chem. Look back at your Chem 1 notes. There's also plenty of YouTube videos, you know, Khan Academy, Bozeman Science, all those guys that can review this stuff for you. Okay? All right. So now we're going to move on and talk about like everything since we talked about emission, like the beginning of all of this electron arrangements. Nothing is new. All of this has been stuff you learned back in first year chemistry. Starting on page 4 is going to be new stuff. Okay? We need to review some of the background stuff, and now we're going to add in a new layer. All right. So, silicon. Let's draw its orbital diagram. And remember what I said before? Typically, I'm never going to ask you the full orbital diagram. For the orbital diagram, all I'm really going to care about are the valence electrons. So let's write out first silicon's core configuration, or its noble gas configuration. How many electrons does silicon have? 14. Okay. Which noble gas are we going to use? Neon. So Ne. And then what's the rest of its configuration? 3s2, 3p2. Good. So let's draw the orbital diagram for this. for 3s2, 3p2. And this is the thing with like the lines and the arrows, or you might have drawn boxes with arrows in them. This is that stuff, okay? So 3s, remember, this is an orbital diagram, so we're signifying the different orbitals of those sublevels. So 3s has how many orbitals? S has one orbital. So S, this is 3s. How many electrons are in that 3s? 2. And there's an up arrow and a down arrow. And I normally just do half arrows because they're faster. Question. Did it matter if I drew the up arrow first or the down arrow first? Back in first year chem, you were probably told, yes, it does matter. Always do the up arrow first. And I do that too, because we're trying to just teach you the basics at that point. And it's so much easier just to follow rules. But honestly, it doesn't matter if you do the down arrow first or the up arrow first. It doesn't matter. So, sorry. Now 3p. 3p, how many orbitals? 3. That's because it's a p sublevel, not because it's the third energy level. How many electrons are going in the 3p? 2. And Hund's rule states that you need to put electrons in, electrons will enter empty orbitals with parallel spin first before they begin pairing up. So, how many electrons go? 2. They're not going to share an orbital because we have 3 orbitals available in the 3p. As long as you have 2 electrons with parallel spin, you've done it correct. Convention states to do it like this, right? That's what you learned back in first year chem. What if, oops, didn't mean to erase most of my orbital there. What if I did this? I'm not wrong. I'm still following Hund's rule because my 2 electrons are in separate orbitals within that same sublevel and they have parallel spin. If you want to continue doing what you did back in first year chem, that's fine. That's how I do it just because it's convention and it's following, you know, what we typically do, but I'm just letting you know that if you ever see something like that, it's not wrong. All right. Oh, whoops. Don't know why I drew it way over there. Here we go. All right, so there's my orbital diagram. So the question is this paramagnetic or diamagnetic? These definitions were in your guided notes. Let me write them out, though. Paramagnetic is there's one or more unpaired electrons in the atom. And what this ends up happening, what this causes is that element or that atom can be attracted to a magnetic field. Okay? Diamagnetic is all the electrons are paired. So this one would not be attracted to a magnetic field. Now, I always have the hardest time remembering that diamagnetic means that they're all paired up because paramagnetic starts with pair. And so I always think like paramagnetic, oh, that's all paired. No, it's not all paired. The way I always have to tell myself is diamagnetic means magnetism dies. Okay, magnetism dies, and the only way you can be magnetic is if you have unpaired electrons. Okay, so however you want to think about remembering that. So is silicon para or dia? It's paramagnetic. Because there are unpaired electrons in the 3p. Okay, and you're going to see more of that in your homework. All right. Ready? chromium and copper. We're going to write the core configurations. Remember, that's the noble gas configuration. So let's deal with chromium first. It has 20-something electrons, 24. All right. Which noble gas are we going to use? Argon. What comes after argon? 4s2, 3d, 4. Right? Let's draw out the orbital diagram for the valence. So 4s has how many orbitals? 1, with 2 electrons. And then 3d has how many orbitals? 5. Then we'll just stick with the normal, good old-fashioned Chem 1 way to do it. What if I told you that's wrong? It's wrong. This is one of the exceptions that I was talking about. Don't erase anything. I want you to leave it like this. What really happens is when that last electron is being filled, or when it's filling the electrons, instead of, remember when I said how 4s has slightly more energy than 3d? But it's only slight. They're really close in energy. Notice how the 3d has 1 empty orbital. It is a stabler configuration for this electron here to not be there. It is more stable for it to be here. It's a little bit, the electrons are at a slightly lower energy for that sublevel to be half filled. So really, the orbital or the core configuration is AR 4s1 3d5. And it's not an excited state. In a little bit, we're going to talk about the difference between excited and ground state configurations. This is not the excited state. This is the ground state. Ground state just means that that the electrons are occupying the lowest energy orbitals available. This is the lowest energy orbital available for chromium. And this happens with chromium and molybdenum and tungsten and seaborgium. Happens with that entire column from the D block, where it's like almost half filled. Oh, let's just move it over. And it'd be whatever S1, whatever D5. Okay? And again, that's the ground state. That's just what it does. Back in first year chem, I always try to avoid the exceptions as examples in first year chem because I can't, myself, I just can't write it. I can't accept 4s2 3d4 as the right answer because I know it's not really right, but I don't teach the exception to my academic chem kids. Okay? And I don't think you guys were taught the exceptions either. It was in the notes and research? Okay. Yeah, I think he said that he mentions it, but he doesn't really deal with it too much. Now, copper has 29 electrons. Let's pretend we're first year chem students again. Let's write out its core configuration, its noble gas configuration. We're going to use argon again. And it'll be 4s2 3d9. You can probably predict what's going to happen, but let's draw out that orbital diagram. So 4s with 2 electrons, and 3d, 1, 2, 3, 4, 5, with 9 electrons. All right, what's going to happen? Yeah, so instead of having 2 in the 4s, it's going to have 1 in the 4s and 10 in the 3d. Again, this is the ground state for copper. It's just a little bit more stable for the 3d to be completely filled and have the 4s only half filled. It would still be considered paramagnetic, yes, because it still has an unpaired electron. It's just not in the 3d, it's in the 4s. Okay? And again, this happens with the entire copper family. So silver and gold, and 111 has a name on our periodic table. It's not named up there, but it does have a name. I can't think of it right now. RG, yes. Yeah, I don't know how to pronounce that. Roentgenium. Yeah, whatever. Sorry, person who named that, if you're watching this video. I doubt you are. I don't even know if the person who named it's alive. So, okay. Cool? Exceptions. Now we're going to talk a little bit about what's happening with the electron configuration when we form ions. And this is going to explain, or I'm going to start to explain the transition elements and how we can get different oxidation states. Why sometimes it can be like +2 or +3. You know? Yeah. All comes down to the electron configuration. All right, so let's start off with something simple, like sulfur. Okay, let's first do the orbital diagram for sulfur, and then we'll deal with the ion, okay? And we're just going to do the valence orbital diagram. Or I guess we don't even need to do the orbital diagram. I'll do that with iron. But for sulfur, what is the sulfur atom's core configuration? Or noble gas configuration? Ne. Three S2, 3P4. Okay. So to make it S2 minus, what did it do? It gained 2 electrons. All right, so it's S2 minus. Where do those 2 electrons go? In the 3p. It's going to fill in the 3p. So it'd be neon, 3s2, 3p6. So now its configuration looks like argon. Most elements, when they form ions, they like to have the same electron configuration as a noble gas. Okay, the main group elements, or the representative elements, which are groups 1 and 2, and then 13 through 18, they will do this for the most part. There's a couple exceptions like lead and tin that act more like a transition metal. The transition metals, they won't necessarily look like the noble gas configuration. That's why we get the multiple oxidation states. Okay. For aluminum, there we go. For aluminum, what is its core configuration? Neon, three S2, 3P1. So to form aluminum plus 3, or 3 plus, what did it do? Lost 3 electrons. Which 3 electrons is it going to lose? The last 3, which would be the, yeah, all of these, right? These get lost. So its core its configuration will look like neon, which will be helium and then 2s2, 2p6. So it like drops down in energy level. It lost all of the electrons from the 3rd energy level. It's gone. Okay? This is stuff that you should have been able to do back in 1st year Chem. We always avoided the transition metals because they were weird. Until you get to AP Chem. All right, Fe. Let's do just Fe metal first. It's not an exception, so we don't have to worry about it moving from the 4s to the 3d or whatever. So which noble gas do we use? Argon. And then 4s to 3d 6. 4s to 3d 6. All right. I'm going to draw out that orbital diagram. Iron is a metal. Metals like to form cations. They like to lose electrons. when iron loses electrons, for the transition metals, you're always going to pull from the S first. Always pull from the S first. Okay? So iron, to make it Fe plus 3, or 3 plus, which 3 electrons is it going to lose? It's going to lose from the S, and which one from the D? The paired one, yeah, one of those paired ones. That's why it's plus 3. So its configuration would be AR 4S0 3D5. Sometimes you don't write the 4S0. I'm going to always write it so you know that it was there and then we lost those electrons. Now, iron can also make a plus 2 configuration. It can also make plus 2. I'm just redrawing that real quick. So to make it plus 2, which 2 electrons is it losing? Just the 4s. So it would be AR 4S0 3D6. And you may or may not remember this back from Unit 2, how certain elements, like especially the transition metals, their higher oxidation state is favored over their lower one, and certain ones, their lower oxidation state is favored over their higher ones. There was a saying, it was huge cups cracked. No, as snails fell, huge cups cracked, or something like that. Iron is one of the few exceptions that the higher oxidation state is favored. And let's look at the configuration. The Fe plus 3, it ends up with a half-filled 3D sublevel. That's a little bit more stable than this more than half-filled for Fe plus 2. Okay? But it all comes down to these electron configurations. Okay? All right, we have one more problem to do, and that is number 13. We're going to be looking at the different rules for filling electron configurations and stuff like that. All right, so for each of these, we're going to decide if the electrons are in a ground state, excited state, or impossible state. And if it's excited or impossible, we're going to state which violation of the rule occurred. Okay, so before we go into this, there are 3 rules that we use. And I've mentioned a couple of them already. One of them is the Aufbau principle, that electrons will fill the lowest energy orbital available. Okay, so from the bottom up. The other one was Hund's rule, that electrons will fill, like if there's multiple orbitals for a sublevel, they'll fill one per orbital with parallel spin before they start pairing up. And the third rule is the Pauli exclusion principle. And that is no 2 electrons can occupy the same space, meaning that 2 electrons in an orbital have to have opposite spin. If they have the same spin, they're technically in the same space, which doesn't work. Okay? If Aufbau or Hund's are violated, that's excited state. If Pauli exclusion principle is violated, it's impossible. So that's the one that is impossible to violate. All right, so this first one, what type of orbital is represented here? Or what type of sublevel? An S. And then what type of sublevel is represented here? What type of sublevel is represented here? A P. Doesn't matter if it's whatever number, we have an S and a P. What state is this configuration in? Ground. Normal ground state. So did we have a rule violation? Nope. All right, this one's also S and P. What state is this in? Excited. Notice how in the P sublevel, we have an up arrow and then a down arrow and then an up arrow. That's the excited state because they don't have all parallel spin. So we violated Hund's rule. All right, our third one is S and P again. But why is that the impossible state? Because we have 2 electrons in that S with the same spin, which is impossible because we violated the Pauli exclusion principle. Okay. All right, our fourth one. This one's an S. What is this sublevel? D. So what state are we in? Excited state because of this down arrow right here. So this one's just like our second one. We violated Hund's rule. Like I said, violating Hund's rule or the alpha law principle is not bad. It's just that's excited. Okay? And next one, we have S and P. Impossible because we have our 2 down arrows together. Physics doesn't like that. Violating the PEP. That's bad. Orange. All right. The next one. We have an S sublevel and a D. What state is this in? What? Why is it ground state? This is like what we were talking about here. Let me go back. Here. This is just like the chromium family. Remember? We were filling in the S, and instead of having our last electron going down in the S, it's just so much easier to go into the D. So this is still ground state. So we didn't violate a rule here. This is just the chromium family. This is representing some element from that chromium group. Chromium, molybdenum, tungsten, or seaborgium. All right, and then our last one, we have S and P, and this is excited state. Which rule did we violate here? Aufbau. It's A-U-F-B-A-U. And that is not someone's name. It's just a German word that I think means like from the ground up or to build up. So let me talk about this one. It looks like what we were talking about with copper, right? Where instead of filling in the S, we're just going to put it in the P. But those exceptions are only for S and D. And there are some that in the F block that do it as well. Remember, the S and the D sublevels, like 4S and 3D, they're really close in energy. But 4S and 4P, they're really far apart in energy. I like to think of it this way. Going from S to P, the energy difference is like the energy it would take to jump over the Atlantic Ocean. Going from S to D, the energy difference is like jumping over a 1-foot puddle. It's real easy to jump over that puddle. I would love to see you try jumping over the Atlantic Ocean. Okay? Yes. It's a German word. It just means like from the bottom up. Oh, that you're going to fill the lowest energy orbital available. Okay? So like this chromium family, it's not a violation of the alpha principle because technically that 1D has the D orbital that we were using has slightly lower energy than the 4S because it's a slightly more stable configuration. Okay? All right. So I'm going to stop the recording.